G'day, welcome back to Mathematics. Today we are finishing off our 2024 HSC exam series, taking a look at the Advanced Maths exam. Going to run you through a few of my favorite or more challenging questions from the exam and just give you as much guidance and advice as I can fit into a half hour. Hope that'll help you prepare for your upcoming exams. Thanks for joining me. Let's get into it with a question from the multiple choice. We're going to look at multiple choice question 6, which was at a band 4 level. We're asking to find the domain of the function 1 over the square root of x squared minus 1. Okay, the way I like to approach domain questions, which are pretty common in the HSC, is I like to try and think about what can x not be. So we're trying to avoid breaking some of the laws of mathematics. A few of those laws include we cannot do a logarithm of a negative number, which is not going to be relevant for this question. We also can't do the square root of a negative number, that gives us no answer, and we also can't divide by 0. So these last 2 points are going to be very relevant for this question, where we have a fraction and we have a square root. So we don't want the bottom to be 0, and we also don't want the inside of the square root to be negative. So that guides us towards the fact that x squared minus 1 needs to be positive for the domain of this function. So we're going to figure out what x values, squared and minus 1, are going to give you a result greater than 0. One way you can approach this is by thinking graphically about what the parabola x squared minus 1 looks like. That's a concave up standard parabola shifted down by 1 unit, which looks like this. Now, if you're trying to see where this parabola is greater than 0, you're trying to see where it is above the x-axis, and we can see to the right of 1 and to the left of negative 1, the parabola is trending up above the x-axis. So from that, you could say we want our x values to be greater than 1 or less than negative 1. Or if you prefer an algebraic approach, you can add the 1 across in the inequality. And now you can say, well, if I'm squaring something and getting an answer bigger than 1, either I'm squaring a number that's bigger than 1 or I'm squaring a number that's less than negative 1, which then goes back to being positive. So either graphically or algebraically, we figure out that x needs to be above 1 or below negative 1. And so B and D are both sort of trying to say that using this interval notation. However, with B, we have the square brackets on negative 1 and 1, meaning that they are being included, but we can't include 1 because that would give us a 0 inside the square root, and then we would be dividing by 0. So we want to exclude the 1 and the negative 1, and that's why option D is the best option, because we have from negative 1 up to from negative infinity up to negative 1, and then union of that with 1 to infinity, not inclusive. So D is the pick for our 1 mark in question 6. Okay, let's now dive into a few of my favorites from section 2. We're starting off with question 22a. For 3 marks at a band 5 level, we have the graph of the function log of 1 plus x squared shown below. For part A, we just want to prove that this curve is concave up between negative 1 and 1 as shown in the diagram. Okay, so when we are wanting to prove some results about concavity, we need to be thinking about the second derivative. The second derivative of a function is how you determine your concavity, and wherever your second derivative is positive, that's where you're going to be concave up. So we are going to take the second derivative of our function and try and explain or prove why that expression is always going to be positive, which makes us always concave up. Okay, so we're going to start off by differentiating the function. Now the function is a logarithm, and to differentiate a logarithm, you're going to need a fraction. So starting off with f dash x, we have a fraction. On the bottom of the fraction goes the inside of the logarithm, which is 1 plus x squared. On the top, you do the derivative of that inside. So the derivative of 1 plus x squared is going to be 2x. So on the top, we have 2x as our first derivative. Okay, now we're going to differentiate again, and if you want to differentiate a fraction or a quotient with x's on top and bottom, we're going to need to use the old quotient rule from the reference sheet. So we'll draw up a little bit of a fraction, and for our quotient rule, we start off with the bottom of the fraction, which is 1 plus x squared, and then we multiply that by the derivative of the top, and the derivative of 2x is going to be 2. So we have bottom times derivative of top. Now we do the reverse of that. We're going to do the top times the derivative of the bottom. The top is 2x, and the derivative of the bottom is also 2x, because when you differentiate 1 plus x squared, you get 2x, of course. So we have 2x times 2x on the end. Now for the bottom, you do the original denominator and you square it. So bottom squared is 1 plus x squared, all being squared. Okay, we have our second derivative. Let's try and tidy this up a bit. Let's expand out the bracket on top. So this becomes a 2 plus a 2x squared. And on the end, our product of 2x and 2x is 4x squared. Now I can collect like terms because 2x squared take away 4x squared is minus 2x squared. And because I'm feeling a little fancy, I may even factorize the top by taking out the 2, leaving me with 1 minus x squared. Okay, now remember the goal of this question for 3 marks is to prove why the second derivative right here is always positive. So we've got a 2 up top, which is always positive, and on the bottom we have 1 plus x squared being squared, which is always positive because it's a number being squared. It always gives you 0 or above. So all we really need to make the argument for now is why the 1 minus x squared is positive, given that x is between -1 and 1. Okay, so let's try and build up to that. Let's start with x being between -1 and 1. Now let's think about what happens when we square that. When you take a number between -1 and 1 and you square it, the result is always a number between 0 and 1. So we're going to say that x squared is between 0 and 1 because we're trying to build up to 1 minus x squared. So if x squared is between 0 and 1, that means that 1 minus x squared, well, we're doing 1 and we're taking away something that's less than 1. So this is always going to be a positive result, okay? Because x is between these two numbers, x squared is between 0 and 1. So 1 minus x squared is always going to give us a positive result. So therefore, the top of that fraction is always positive. We'll do a quick explainer as to why the bottom is positive now, because x squared is always positive. When I add 1 to it, it's going to be something bigger than 0. And so then when I square that, it is of course going to be a positive number. So here's our little algebraic argument for why the top and bottom of this fraction are both positive. Therefore, the entire fraction is positive. Therefore, our second derivative is always greater than 0, which means that the function is concave up between these two values. Done and dusted. Okay, so that was fun. That was question 22. Up next, we've got a financial series question, which I haven't done a lot of these on the channel because they frankly take 1,000 years and they're very, very hard to animate. But let's have a crack at this one. We have Jack depositing $80 into a savings account on the first day of each month for 24 months. Interest rate is 6% per annum and we are compounding monthly. We want to find how much money we will have at the end of 24 months. Okay, so we're trying to find the final value of this annuity over 24 months. So straight away, we are compounding monthly, which means all of our calculations are going to be in months. So we're going to start off by turning our per annum interest rate into a monthly interest rate by dividing it by 12. So 6 divided by 12 is a half, so we have 0.5% of interest each month throughout the year. Compounded monthly, which means we're using the compound formula, of course. So we have our future value formula right here. And let's think about what happens in the first month. First month, we put $80 into the savings account, and then it accrues 0.5% of interest across the month. So putting those values into this red formula, we have the amount at the end of the first month is the $80 that we put in at the start. We then have the 1 plus 0.5% for our 1 plus R, and our power of n, this is just working over 1 month, so we have a power of 1. Okay, let's simplify the inside a little bit. 1 plus 0.5%, we can write that as 1.005, and here is the amount owing at the end of the first month. Okay, so now in the second month, we are going to add in a new $80. So we're going to plus 80 here, and then that entire figure is going to get interest over the month. So we need to multiply this entire figure of this plus 80 times that by the interest factor in the second month, which is once again going to be 0.5%. So once again, we're going to be multiplying by 1.005. So there's our second month setup. We have the first month value. We then add in another $80 and then multiply by the interest factor. Okay, we're just going to expand and simplify this a little bit and make it look more like a pattern that we're trying to build together. So expanding this out, we have 80 1.005 to the power of 2, and then 80 times 1.005. So here was our amount after 1 month. Here is our amount after 2 months. Hopefully you're starting to see a bit of a pattern forming, and you can sort of extrapolate that the amount owing at the end of the third month is going to look like this. If we factor out the 80, we get an even more clear series, and we can then jump to month 3 and say, cool, if this is month 2, then month 3 is going to have an 80 at the front, a 1.005 to the 3, plus to the 2, plus to the 1, and there is our setup. Okay, so once you've done a few iterations of this, sometimes 2, sometimes 3, you can see the pattern forming, and you can extrapolate this pattern to fill out the entire 24 monthly period. And we'll say the amount after 24 months will be 80 multiplied by 1.005 to 24 to the 23 to the 22, etc., all the way down to power of 1. Okay, so there is our setup. Now we're going to use some information about series to evaluate what the sum of this series is, so we can then multiply this by 80 and get our final answer. So what we have here is a geometric series. The difference between each terms is a common multiplier of 1.005. So that is the definition of a geometric series. So we are going to set it up and say this is a geometric series where our first term is 1.005. We're just going from right to left. So this is our first term. Power of 2 would be the second term, and then power of 24 is the last term. So A is 1.005. Our R multiplier is also 1.005. That's how we're getting between each of the terms. And our number of terms is 24. So now we reach for the reference sheet and we write down our sum of a geometric series formula, which looks like this. So we have sum after n months is initial value r to the power of n minus 1 over r minus 1. Putting in our information, we have A is 1.005, we have R to the N is 1.005 to the 24, and then on the bottom we have 1.005 minus 1. Okay, so this calculation will add together all 24 terms in this series for us and give us a total. Now when we find this total, we want to multiply this by 80 so we can then find the amount owing after 24 months. So taking our series formula, multiplying the result by 80 gets us our total value or a total amount in the account after 24 months, roughly $2,044.73. Okay, so if you're new to these questions, this is how you set it up. Build your pattern, get your series, and then use your series formulas to find the answer that you need. And that's question 24. Up next, what do we got? Question 25, right next door, is a function which is defined by these three scenarios, and we have h being a constant. So for the first part of 2 marks, we're going to do all 3 parts of this question. We want to find the value of h that makes this function a probability density function. Okay, so some properties of PDFs that we can use to figure out this question is that we're supposed to know that the total area under this curve between 0 and h needs to be 1. That's the definition of a probability density function. It creates an entire sample space of 100%, which is equivalent to 1. So to figure out question A, what we can do is integrate our expression here, because we're finding the area, integrate 1 minus x over h between its 2 boundaries, which are 0 and h, and we can set that equal to 1 because we know that it is a PDF. So that's how we're going to start. Take our function, integrate between 0 and h to apply this property here. So we have 0 to h of 1 minus x over h, and that's got to be equal to 1 for this to work. Okay, so let's do some integration. 1 integrates to x, and then the x integrates to x squared over 2. So that over 2 is going to go down there with the h and make a 2h. So 1 going to x, x squared divided by 2 looks like that. Our limits are h and 0, and the answer is 1, and we are going to solve for h. So fortunately, when we sub in 0, everything just turns into 0, which is nice and friendly. So all we really need to do is sub in the value of h. So doing that, we get h minus h squared over 2h. And then the second limits, as I said, just give you 0, so we can just ignore those for now. Okay, h squared over 2h is going to simplify to be h over 2. And now what we have here is 1h, take away a half h, which gives us a half h. Multiplying the 2 across, we get our 2 marks answer of h is equal to 2. Okay, on to part B. Now that we know that we can put a 2 there and we can put a 2 there, we can proceed with part B, which is asking us to find the formula for the cumulative distribution function and then sketch its graph. I believe this was 2 marks, 1 mark for getting the CDF and 1 mark for the sketch. And the sketch was the hard part, which we'll talk about. Okay, so the CDF is a function that basically tells you what percentage of the curve is up to and including that point. Okay, that's why it's cumulative. It's up to and including that point. Now, the way you want to find that is you want to integrate your PDF like we did originally, except we're going to start from our first value, which is 0, and our second value we're just going to keep as a generic variable x. So I'll show you what I mean. And our notation here is that the CDF, we use a capital F, and we're just integrating our original function from the first value of 0, and then we're keeping the second value as a variable, so we can then use it as a function. Okay, so very similar integration to what we just did. We're integrating once again 1 minus x over h, except now that we know that h is equal to 2, we can actually get an answer here. Okay, so integrating, once again, the 1 turns into an x, and the x turns into an x squared over 2, which makes x squared over 4. Once again, subbing in 0 is just going to get us zeros for both values, so it's not going to do much, and we don't really need to sub in x because these are already x's. So what that looks like is we just have x minus x squared over 4 taking away 0, and so there we have our cumulative distribution function. So it's just the pre-integrated version of your PDF ready to go. Okay, so now we need to do the hard part, which is to sketch the graph. So if we look at our CDF that we've now made, it basically says that anywhere before x is anything to the left of 0, we're going to have no probability value. Now anything between 0 and 2, which were our 0 and our h value, we have our function here. And then because it's basically finding how much of the curve you've graphed so far, once you get to the endpoint, which is 2, you've graphed the whole thing. So that ends up being 1. So it's 0 before your domain, it's your CDF in your domain, and then at the max of your domain, it's just 1 henceforth. So we're going to have nothing before x equals 0. We're going to be sketching this parabola between 0 and 2. And then from 2 onwards, we're just going to have a straight line at y equals 1. Okay, so what does this look like? It's a parabola. We know that. We also know that it's concave down because it's a negative x squared. So putting that together, we're going to have nothing. And then we're going to have a concave down parabola between 0 and 2. And then from 2 onwards, we'll just have the line y equals 1. So here's what that looks like. We have nothing on the left of x equals 0. We have our concave down parabola, and then at our point there, where we get to x equals 2, that's where we get y equals 1, and then we have y equals 1 for the rest. So the feedback from the markers last year is that the students were pretty good at finding this equation. They were pretty good at graphing it, but a lot of people forgot that from the right there, it needs to be 1 for the rest of it. I think people just sort of left that blank from there. So hopefully, if you get a question like this, you won't make that mistake because now I've pointed it out to you. Okay, I think there's even a part C for this question. Part C is to find the value of the median of the probability density function f of x. Give your answer correct to 3 decimal places. Okay, so we know that the entire area under the curve is going to be equal to 1 because it's a PDF. If we want to find the median, we're trying to find the point where we get up to the halfway point, and the halfway point is 0.5. So because we already have our CDF ready to go, what we can do to find our median is we can set this equal to the answer that we're trying to achieve, which is 0.5, and we can see the value of x that gets us to that halfway point. So that's how we find our median. You set your CDF equal to 0.5, and we're trying to find, I'm going to let it equal m. You can leave it as x if you want to, but I'm going to set x equal to m, and then set the answer equal to 0.5, and then solve for m. So we have m minus m squared over 4 is equal to 0.5, and we're just going to solve this quadratic. We're probably going to start off by multiplying everything by 4. So now m becomes 4m, this m squared is now not a fraction, and 4 times a half is 2. Now bringing everything over to one side to make a more friendly quadratic, we might actually bring these guys over here to make the m squared positive. So m squared over here becomes positive, 4m over here becomes negative, and then the 2 is still positive. So our quadratic that we end up with is m squared minus 4m plus 2 equal to 0. Okay, now this quadratic, this cannot be factorized, so you can either go ahead with the quadratic formula if you feel like it. If you're a bit brave like me, or maybe stupid, you might be thinking, why don't I just complete the square? And that's what I'm going to do. I'm going to add 2 to both sides of the equation, because now the left-hand side is a perfect square, and I can factorize it using one bracket. I can factorize this as m minus 2 all squared. And now to solve for m, I can just take the square root of both sides to get me m minus 2 equal to positive or negative root 2. And then I can add the 2 across, and I get my value of m. Okay, now the issue here is that I have 2 answers. I have 2 plus root 2, and I have 2 minus root 2, and the median is going to be in one spot. So if you think about this, the curve we were originally working with was defined between 0 and h, and we figured out that h was 2. So we're only really looking at x values that are between 0 and 2. So we should see which of these 2 answers is between 0 and 2. Now 2 plus root 2 is going to be bigger than 2. So the answer that we want for this one is the 2 minus root 2, because we need to be between 0 and 2. So 2 minus root 2 is our correct answer for m, and that is our median in this probability density function. Wasn't that fun? Okay, now we're into the really scary section of the exam, getting towards the back end. We've got question 29. It's a 4-mark question. It's a lot of fun, and it's a band 5. Okay, we have a quadratic, ax squared, bx, and c. A is not equal to 0, so it is a quadratic. At a particular point, the tangent and normal to the curve are given by this equation and this equation respectively. We have a minimum turning point at x equals -4, and from that information we want to find the values of a, b, and c. Okay, let's make some room and do a bit of summarizing. So we have our equation up here, we have our tangent equation, and we have our normal equation, and these two are both at the same point on the curve. And we know that we have a minimum turning point at -4 for x, and we want to find a, b, and c. Okay, there's a fair few things we can do here, and there's a fair few places we can start. What we definitely want to figure out is a point on this curve. So far, we don't have anything except that we know that x equals -4 is a point, but we can't really sub that in because we don't know what a, b, and c are. A crucial bit of information we can use here is that, like I said, the tangent and the normal are both meeting at a point on the line. What that means is if I solve these two equations simultaneously, I should obtain an x value that is a point on this line, and that's going to give me useful information to solving this question. So that's where I'm going to start. I'm going to set the tangent equal to the normal, and I'm going to try and solve this equation for x to figure out the point on this line. Okay, so solving this, I'm probably going to get rid of the fractions by multiplying everything by 2 to start off with. So we have 4x plus 6 on the left, and on the right we have -x, take away 4. Now we can add the x across to make 5x, and we can subtract the 6 across to make -10. And now we can divide by 5 and say x is equal to -2. Okay, so these 2 points are meeting on the curve when x is equal to -2. I can sub that -2 into either of these two equations, and it's going to get me the y value as well. So I'll have a coordinate that both these lines go through, and it'll be a coordinate on our curve. So subbing into the nice one, which is the tangent, I get 2 times -2 plus 3, which gets me an answer of -1. So I know that -2, -1 is a point on this line. That's going to be really useful. Okay, so here's what we're dealing with. We have a curve like this. We have a minimum turning point at -4, and our tangent and our normal just crossed over at -2, 1, like this. Okay, so what else can we do from here? We're probably going to have to do something calculusy with this minimum turning point. So let's go to that next. Okay, so we're going to take the derivative of the curve, differentiating y equals ax squared plus bx plus c, bringing the 2 down the front to make 2ax, differentiating the bx to be b, and then c just becomes 0. Now, what's good about this is I know that I have a minimum turning point right here when x is equal to -4. And at your minimum turning point, that's where your derivative is equal to 0. So I can sub x equals -4 into my derivative, and I can set this equal to 0 because I know it's a minimum turning point. So at x equals -4, the first derivative is 0. So we get 2a times -4 plus b is equal to 0. So this gets me -8a plus b is equal to 0. I'm going to label that equation 1 because we're going to figure out another equation very soon that we can figure out to solve these two together. Okay, so what else do we know? Well, we have a tangent right here. Okay, the tangent has a gradient of 2, as we can see in the red line right there. What that tells me is that the gradient of the curve at the line x equals -2, which is right here. Okay, at that point, the gradient of the curve is equal to 2, because that's the gradient of the tangent. So what that means is I can go back to my derivative equation and I can say, cool, I can now sub in x equals -2, and I can set the derivative equal to the tangent gradient, which is 2. And so as you're probably noticing, this is a pretty hectic question and we're just over halfway. So putting that information in, I get 2a times -2, putting my x value in here and setting my derivative equal to 2, gets me -4 plus b is equal to 2, and we have our second equation. Okay, so looking at equation 1 and equation 2, I'm seeing that they both have a b in common. So if we subtract these two equations, we're going to eliminate that variable and we can solve for a. And I'm going to have a drink before I start coughing everywhere. Too late. Okay, so let's do equation 2, take away equation 1 to try and keep everything a little bit positive. Making some space, equation 2 minus equation 1, we're going to be doing -4a, take away -8a, which is going to give us +4. B take away b is 0, and 2 take away 0 is 2. So we end up with 4a equal to 2, which then tells us if we divide both sides by 4, we get a is equal to 1/2. So we are 1/3 of the way there. We have figured out what a is. Okay, now what can we do with this? We can put it into our simultaneous equations. We'll probably put it into equation 1, and we can solve for b. Oh, I put it into equation 2. That's weird, but that's going to work anyway. So where's equation 2? Right there. So we've got -4 times 1/2 plus b is equal to 2. -4 times 1/2 is -2. And so if we solve this for b, we're going to be adding that -2 across, and we get that b is equal to 4. Okay, so we have 0.5, we have 4, we have 2 of the 3 confirmed. Now, what's the easiest way to figure out what the C is? Well, fortunately, in this middle column here, we did all this work to figure out that when x is equal to -2, the y value is equal to -1. This is really useful because now I can go to my equation. Now that I know what a and b are, I can sub in x equal to -2, I can set y equal to -1, and I can then solve for c, and I'll have this 4-mark question done and dusted. So we'll make some space, we'll get our point, we'll get our a and our b, and we're going to say, here's our equation so far. I've just got a as a half there, and I've got b as 4. And now we're going to say, when x is equal to -2 from our point, y is equal to -1. So we set the other side to be -1, we sub in x equals -2, and then we just solve this for c, which is the easy part of this question now. We have a half times 4 here, and we have 4 times -2. So we end up with 2 minus 8, which is -6. Add the -6 across the right, and we end up with c equal to 5. And therefore we have a, b, and c done and dusted. We have our equation, and we have our 4 marks. Okay, that was fun, but it was a lot of work, and we had to figure it out all for ourselves. We need to run through all this information, figure out how it applies, and yeah, really tough question. What could be tougher than that, I hear you ask? Well, actually, question 30 is a band 6 question about geometric series, and that's the last one we're going through today. Suppose the geometric series x squared, x cubed, etc. has a limiting sum s. By considering this graph or otherwise, find the range of possible values of s. Okay, deep breaths, we can do this. All right, we have a geometric series. We can see the first term in our geometric series is x, and we can see our multiplier, which is r, between each of our terms is also x. Now, crucial information, it says that this series has a limiting sum s. Now, only some geometric series have limiting sums. You only have a limiting sum when you are multiplying by something that's less than 1. So you're making the term smaller as you go along. So from that tells us that because r is between -1 and 1, like I said, the multiplier has to be making it smaller, but it can also be making it negative. So it can be between -1 and 1, and our r value is x. So we know that x is going to be between -1 and 1. Now, because we have a limiting sum, we can use our limiting sum formula, which is on the reference sheet, and we can say a is our first term, which is x, and our r is also our x, so we get x over 1 minus x. Okay, and now here's the tricky part. The tricky part of this question that I think made it such a high band question last year is that x over 1 minus x is actually the same thing as -1 minus 1 over x minus 1. These two equations are the same thing. It's just not very easy to see. So the next part of this question, which is the tough part, is me trying to explain why this equation and this equation are actually the same thing. So first of all, this one has a 1 minus x on the bottom, and this one's got an x minus 1. So I need to swap the negatives there. So I'm going to take the negative out of the bottom of this fraction and just bring it out the front. So now the x is positive and the 1 is negative. Now it looks a little bit more like what we're trying to go for. Okay, because we don't want an x on top, we want a 1 on top. Here's the trick for that one. We're actually going to add and subtract 1 to the top of this fraction. Now that seems very strange, and it seems like I absolutely pulled it out of my ass, but here's why that's very cool. Because I can now split these two fractions apart, and one of them is going to have an x minus 1 on top and bottom. I'll show you what I mean. We're going to leave the negative out front for now because it's kind of scaring me and I don't want to deal with it yet. Leaving the negative out the front and splitting this fraction into two subfractions where one of them is an x minus 1 on top and bottom and the other one is a 1 over x minus 1. Okay, that's the key here for splitting this apart and getting it to look like this. Okay, now top and bottom of this thing are the same, so this turns into 1, and so we end up with a negative of 1 plus 1 over x minus 1. Expanding out the negative, we end up with negative 1 minus 1 over x minus 1, and so there is your proof that this fraction and this expression here are mathematically equivalent. That was pretty tough. I feel like if you wanted a little bit of easier version of that question, you could start with this and then combine the fractions and show that you get this. So potentially starting with this one and working towards that one will be an easier option if that working out there is scaring you, because it is scary. Okay, so where we've arrived is that this is our expression for the limiting sum of our expression. And now that tells us we want to look at the graph of this. So let's think about what this graph looks like. Let's start off with some basic graphing lessons. Here is what the hyperbola 1 over x looks like. Ta-da! I call this the butterfly graph. It's got a couple of asymptotes, and yeah, hopefully you've explored this in class before. Okay, what happens when I change the x to be an x minus 1? Well, this takes the entire graph and shifts it 1 unit to the right. So now the asymptote, the vertical asymptote, is at x equals 1. Okay, what happens when I put a negative in front of this? Well, this is going to reflect the graph across the x-axis, so it's going to flip it upside down and look like this. And now the last step is to add in this minus 1. And so if you're adding in a minus 1 to your expression, it's taking the entire graph and shifting it down by 1 unit. So there are our 3 transformations to get from 1 over x to this expression here. And so let's just sort of blow this up and look at this graph. That was the one from the right. Okay, now the red line is showing us the possible values of the left-hand side, which was s. But the crucial information here is that the question said we have a limiting sum, and that means our x value, which is really our r value, is between minus 1 and 1. So we are only looking at these sections of the graph. So in this blue section, where our multiplying factor is between negative 1 and 1, we can see our red value for s is going as low as negative 0.5, and it's going as high as infinity. So the ranges of values of our sum of this geometric series is between negative 0.5 and positive infinity, and that is your 3 marks answer in this Band 6 question. Oh my god, I'm exhausted. It's a Sunday, and frankly, it's been a long weekend. But hopefully, you got some value out of that, and that helped you feel a little bit more comfortable for your exams. And that's a better way of writing your answer, and that's done and dusted. Anyway, if you made it to the end of that, thank you for joining me. And yeah, like I said, hope that helped you out getting ready for your HSC. And yeah, hopefully I can get some more videos out between now and your exam. They're going to help you build some confidence and yeah, smash the exam. Please like if you found it useful. Chuck me a follow on Instagram and send me some questions if you're struggling. DMs is the best way to get a question straight through to me, and I'll get back to you with an answer as soon as I can. But other than that, thanks for watching. Catch you in the next video, and goodbye for now, not forever.